Hi everyone. In this video, we're going to talk about different types of graph symmetries and how we can determine these symmetries when we're given an equation. So first thing is, what is symmetry? And so to answer this question, I'm going to provide you with an example. So if I were to consider this flower shape, I can see that the flower is balanced and it looks very similar on all sides. And if I were to divide it down the middle vertically, what I have on the left side looks an awful lot like what I have on the right-hand side. And I could say the same thing for the top and bottom of my flower. What's on top looks a lot like what's on the bottom. And so if I looked at this on a coordinate plane, so let me label and draw my axes here. So horizontal is our x, vertical is our y. And if I were to compare my flower across the y-axis, I can see that the tips of my petals, so this one on the left and the one on the right, they are at the same height. Or in other words, I can connect them with a perfectly straight horizontal line. Same thing with the petals on the bottom half of the flower. The tips of them are at the same height, straight across from the y-axis. So in other words, I can say that this flower shape is symmetric. And specifically, if I wanted to use my math terms, I can say that it's symmetric about the y-axis. And the reason is because if I were to fold my flower on the at the y-axis, then these points of my petals would align perfectly on top of one another. And so when we're looking for symmetry in graphs of equations, we're checking that the features of one part of the graph are a reflection or a mirror of another. And there are going to be three forms of symmetry that we're going to look for. And so here we have a table. So the very first one that we're going to focus on is if we're symmetric with respect to the y-axis. So here I have a parabola drawn. And I've highlighted 2 points, -2, 4 and +2, 4. And so if I were to fold my paper along the y-axis here, then these points would align perfectly with one another. So in other words, another way for me to say this is that if there's a point xy on my graph and it's symmetric with respect to the y-axis, then my graph also has the point -xy, which we see is true for this parabola. We have +2, 4, so we also have the point -2, 4. And we can test an equation, so if we weren't given a graph like this, we can test the equation to see if it's symmetric with respect to the y-axis by substituting in -x for x and seeing, do we get the same equation back? So if I wanted to write this in different notation, if I plug into my equation a -x, I should get our original equation back, or the same as if it was +x. If we're looking for symmetry with respect to the x-axis, well, let's look at this graph here. This time I have a parabola that's turned on its side, and I've highlighted the points 4, 2, and 4, -2. Well, here, if I was to fold my graph on this x-axis, I could see that my points 4, 2, and 4, -2 will align perfectly with one another. Another way that I can say this is if there's a point xy on my graph, then there's also the point x -y on the graph, which again is exemplified here with these points that I have. I have a 4, +2 on my graph, so then that means that I should also have a 4, -2 on my graph, which I do. And if we're going to test an equation to see if the graph would have this type of symmetry, then we're going to substitute a -y in for our y and see, do we get the same equation back? So in other words, if I have a negative output and I did some simplification, then I should get my regular equation back in order for it to be symmetric with respect to the x-axis. If we're looking to see if a graph is symmetric with respect to the origin, this is a little different from our previous two types of symmetry. So here, I have highlighted the points 1, 1 and -1, -1. So if I spun my graph around the origin, remember the origin is 0, 0, it's where our x and y axis intersect. If I were to spin this around the origin 180 degrees, then my graph should be the same. They should overlap. And another way I can say this is that the point 1, 1 is on here, so then that means, which is xy, that means that the point -x, -y, or in this case, -1, -1, should also be on the graph. Another way that you could talk about symmetry with respect to the origin would be that it's symmetric across, if you were to do symmetry across the x and the y axis. So like if I were to reflect this across the x-axis and then reflect it across the y-axis, then our graphs overlap, which would also be true. But you could also think of this as rotational symmetry. So if I rotate my graph about the origin, I should get the same thing. And then if I wanted to test an equation for this, we need to not only substitute a -x in for our x's, but also a -y in for our y's. So again, in this same notation, if I have a negative input or a -x, and I negate the output or our y's, then we should get our original equation back. Notice that for our symmetry with our flower, I mentioned that it's symmetric with respect to the y-axis, but it's also symmetric with respect to the x-axis and with respect to the origin, because if I spun it 180 degrees, it would still overlap with itself. And so this is an example of how we could actually have a graph that has all three forms of symmetry. It's symmetric with respect to the y-axis, the x-axis, and the origin. So when we start talking about or going through our example of testing an equation to see if it has or what types of symmetry it has, we need to do all three tests. If we don't, then we could miss a type of symmetry. So just because you found that, oh, it happened to be symmetric with the y-axis and that was the one that I tested first, I'm done. No, that's not the case. You still have to test for the x-axis and the origin because it could be symmetric with more than one of these lines or points. Okay, so make sure you're testing all three. Another thing I want to note is that if we are symmetric with respect to the x-axis, that means that our graph isn't a function. And if you'll remember, a function means that for every output, we have a unique for every input, we have a unique output. So for every x, there is one y. Well, if I look at this graph, I have two y's or 2 points for every x. So this one in the middle with respect to the x-axis, not a function. So why are we looking at different types of graph symmetry? Why is this important? Well, in this course, we are going to learn about something called even and odd functions, which is actually determined by the symmetry of a function. So when we begin graphing equations by hand, we're going to be able to use properties of even and odd functions, which is going to make our life a little easier because we're going to be able to identify some behaviors at the end of our graph, which is going to minimize the number of points that we're going to have to plot and find by hand. So that is one reason why graph symmetry is important. Questions that you might be asked in this class. Well, you could be asked about identifying if a graph or a function is even or odd. But for right now, we're just going to look at if we're given an equation, can we identify the different forms of symmetry algebraically, or in other words, without just graphing it. So let's go ahead and look at our example. So here we're asked to determine whether the graph of y equals x cubed plus 1 is symmetric with respect to the y-axis, x-axis, or the origin. So the first thing we're going to do is we're going to test for symmetry with respect to the y-axis. If you reference back to that table, when we are testing for this type of symmetry, we are substituting a negative x in for all of our x's and seeing, do we get the same equation back? So our original equation is y equals x cubed plus 1. And then the very first step I'm going to take is replacing our x with a negative x. So we're going to have y equals, in parentheses, negative x cubed plus 1. Now, you may think, okay, there's not really much I can do because I can't find a value for negative x that's being cubed because we have an unknown there. But we can determine if this value, a negative x being cubed, is going to be positive or negative. So let's do this on the side. So if I have negative x cubed, that means that I am multiplying negative x by itself 3 times. So if I write this out, we have negative x times negative x times negative x. And so if I were to multiply the first two, so negative x times negative x, a negative times a negative is a positive, x times x is x squared. So now I have a positive x squared times a negative x. Positive times negative is negative, x squared times x is x cubed. So this quantity negative x being cubed is actually going to be a negative x cubed. So we can rewrite this and drop our parentheses. So now, if I compare this equation that we had gotten with our original equation, so if I'm comparing these two, one thing I notice is that here my x cubed is positive, whereas here my x cubed term is negative. So they are not the same. So therefore, it's not symmetric with respect to the y-axis. So here we have no symmetry. And again, with respect to the y-axis. All right, so then the next thing that we can test is symmetry with respect to the x-axis. So again, if you consult our table, when we are testing for this type of symmetry, we are substituting negative y in for our y. So here, our original equation was y equals x cubed plus 1. I'm going to replace y with a negative y. Oops. And then, so the only way that I have hope of even getting my original equation back is I need a positive y. And so to undo this negative, I need to multiply both sides of my equation by negative 1. So let me show that multiplication here. So negative times a negative is a positive, so we get 1 times y, which is positive y. And then on the right-hand side, remember, we're distributing this negative 1 to both terms in our parentheses. So negative 1 times positive x cubed is a negative x cubed. And then negative 1 times positive 1 is a negative 1. So then in this case, if we're comparing this with our original equation, not only instead of positive x cubed, I have negative x cubed, but also instead of a positive 1, I have a negative 1. So these are not the same. So in that case, there is no symmetry with respect to the x-axis. So far we've found no symmetry in our graph. But we do have one more test to perform, and that is with respect to the origin. So remember, consulting our table, to test for this type of symmetry, we're substituting negative x in for x and negative y in for y. So Again, starting with my original equation of y equals x cubed plus 1. Now I'm going to plug in negative x for x and negative y for y. Now, if you think back to our test with respect to the y-axis, when we plugged in a negative x, and we determined that this quantity of negative x being cubed is going to be just negative x cubed. We can drop the parentheses. So we can do the same thing here for our quantity negative x cubed. It's just negative x cubed without parentheses. But now, again, if we want to ever get back to our original equation, we need to at least have a positive y. So let's try and undo this negative times our y by doing negative 1 times both sides of our equation. So negative times a negative is a positive, and that's 1 times y, which is y. Again, we distribute this negative to both terms in our parentheses. Negative 1 times a negative x cubed is a positive x cubed, and negative 1 times positive 1 is negative 1. Well, now, again, if we compare what we got to our original equation, we have positive y, we have positive x cubed, but we have a negative 1 instead of a positive 1. So in this case, there's no symmetry with respect to the origin. So just like I had told you before, we can have all 3 forms of symmetry. We can also have no form of symmetry in our graph. And let me show you by graphing this equation. Here's our x-axis, here's our y-axis. Our graph, or our equation is y equals x cubed plus 1. So that plus 1 tells me that that's where we're intersecting our y-axis. And then this is the general shape of x cubed. So there's y equals x cubed plus 1. So if I look at my graph, will you see if I were to fold this on my x-axis, well, these 2 sides of my graph don't match up. If I were to fold it with respect to the y-axis, again, the 2 halves of my graph don't match up. And if I were to rotate this graph across or about the origin 180 degrees, it again doesn't match up, because what we would end up getting is that rotating this 180 degrees, it would come down here, which is not the same thing as what we have on this half of our graph. So therefore, this graph has no symmetry. There are, like I said, examples of where we have all 3 forms of symmetry, which is actually the next example that I encourage you to try on your own. Well, I hope you find this video helpful, and I wish you luck as you are testing for your different types of symmetry in your equations.